Welcome to Instrumental Analysis. I'm Vicki Colvin, and this is Lecture 4. We're starting a series of lectures that's covering error and analysis, an incredibly important topic. Certainly making the measurement to get, for example, how much lead is in a keychain for a kid is important, but just as important is to characterize for the user, for the government, for yourself, how precise and how accurate that measurement is. And that's really what we're going to be covering. Now, in this specific mini lecture, we're going to be tackling questions related to the language used to describe error and the kind of poor man's way of talking about random error. Rather than giving error bars, what we're going to do is just work through instrument tolerances and significant figures. It's kind of a quick and simple way of estimating the error that might be present if you're, for example, reading a procedure and you'd like to know, gee, I wonder how precise it would be if I executed this procedure exactly as written. That's an example where things like significant figures and instrument tolerances can be very useful. So why it's important is, let's say you are interested in how much lead is in this teething toy this baby has in its mouth. And in fact, if you're a United States toy manufacturer, you're bound by regulation to ensure that your products have less than 100 parts per million lead. Well, when you make the measurement, the question is, how precise do you need to be? Is it okay to be, kind of about right? Or do you have to specify the error in addition to specifying the amount of lead that you measured? And the answer is you almost always have to specify the level of precision of your measurement. So how do you do that? Well, first, you have to understand the two different sources of error. And this is really an issue of language. So I hope that with this example and the next few, you'll really be confident when you say something's precise versus saying something's accurate. So let me explain. Okay, so let's say you happen to have a sample that, because maybe you standardize it, you know that it has 100 ppm lead, and that's what's called the true value. Usually in analytical chemistry, unless you pay for a standard from NIST, you don't know the true value. Well, when you make the measurement, what you find is, let's say you make not 10 measurements, you make 10 measurements, but strangely enough, your measurements don't all provide the same value. They actually provide a spread of values. So the first thing you're going to notice is that when you do real-world measurements, you always get what's called a spread. That's kind of the colloquial term for random error. The fact is you have an average value, but there's some data that's smaller than that and some data that's bigger than that, and when you average them together, you get your average value plus or minus a spread. Now, the other thing you're going to notice in this data set is that the average value of the measurements is off from the true value, and this is bias. And if you think about the language that you use to describe this, the bias is an example of systematic error. It's always a one-way error that pushes the measurement too big or too small. But all of the measurements are too big or too small, or when you average them, they're off in one direction or another. In contrast, a random error is all about the spread in the measurement. And so if a measurement's precise, it means that you have a small variation in the measurements. And if it's accurate, it means that there's very little systematic error. So just be careful when you use the terms precise and accurate because they mean different things. So let's go through some examples. So imagine in these examples that the center of the target is the true value, and all the arrows you're throwing at it represent measurements. So over here on the left, as you can see, the data is all pulled to the left. And so this is actually showing a lot of evidence of bias or systematic error. So there's problems with accuracy, although there's clearly also problems with precision. Over here, you can kind of notice it's like there's a downdraft. And so this is also an inaccurate example. And because there's a spread in measurements, it's also not very precise. Okay, in these examples, you can see here, this is highly precise because there's little spread in the measurement, and it's very accurate because it actually hit the center. Over here on the right, I might argue that it's pretty accurate because if you averaged all those numbers, you'd probably end up with the bullseye somewhere about here, which is not that far off, but it's very imprecise. So be clear that you can have accuracy without precision, and you can have precision without accuracy. The two are not necessarily caused by the same factors. And so when you're thinking about error and conveying error, really, you've got to separate those two ideas. And what we're going to really talk about in the next couple of lectures is all about precision, conveying that spread in a measurement, the random error that might be controlling how precise your numbers are. And what we're going to do today is learn the way of estimating that, using instrument tolerances and then communicating it via significant figures. That's not the best way to convey random error, but if you don't have a lab and you're relying on a procedure, it's a perfectly acceptable way to estimate the level of random error that might be present in a measurement. We're going to learn a lot more sophisticated ways of characterizing error, but I wanted to start with the sort of simplest zeroth order way of thinking about error and estimating it, for example, if you were given a procedure. To do that, we have to understand instrument tolerances. And so what I show you here are two examples of how to measure pH. Both of them use instruments. The one on the left costs about $7 and the one on the right costs about $500. And if you're going to use the one on the left to measure pH, well, I don't know about you, but I have pretty good eyesight. I can tell the difference between green and blue. I think clearly that paper looks like it's 10. Of course, it's pegged out at one end of the scale, but you can imagine being convinced that you could tell the pH to plus or minus 0.5 units. So the pH paper is an example where the instrument tolerance is something you decide. And in fact, if you're not, have a particular disability in a lab or you can't do a certain task well, you might actually increase the instrument tolerance to reflect your own inabilities to use the machine, or in this case, a piece of pH paper. So for example, a colorblind person would have a lot higher instrument tolerance in the application of pH paper. Now on the right is true instrument. It's pH meter, and typically they're going to be precise to about plus or minus 0.01 pH units. So that's a much tighter and more precise measurement. And so we'll find usually written on an instrument, or sometimes in the manual, the manufacturer themselves will tell you what the instrument tolerance is, which is kind of the best case random error you could assume if you use that instrument. So those instrument tolerances are really fabulous ways of sort of guesstimating what error might be present if you're actually implementing a certain analytical procedure. So here's some more examples that are very pertinent to, for example, the measurement of lead in baby toys. The first thing you're going to have to do is weigh the sample. And so the balance that you use is going to be incredibly important because it's going to tell you the net weight of the sample, which is actually the denominator of the overall measurement of lead, which remember is parts per million. It's parts per lead divided by the total sample weight. So you're going to have that denominator, and you're going to get that from a balance. And that balance can be very precise. For example, analytical balance can be precise to 0.0001 grams, and it costs $3,000 or $4,000. Or you might have a really small lab and not a lot of money and have to use a pan balance. Well, that's going to be precise to plus or minus 0.1 grams. And so you're going to have a huge difference in the random error that you would estimate based on just the fact you'd use these two different types of instruments. Same is true of volumetric measurement, a really important thing to do when you make calibration standards for measuring the lead in an elemental analysis. And so when you make those calibration standards, if you use high quality analytical glassware, for example, a volumetric flask, you can measure volume to plus or minus 0.01 milliliters. On the other hand, if all you have is a graduated cylinder, it's going to be plus or minus 2 mils. And in fact, as you can see here, if you zoom in, the manufacturer themselves tell you plus or minus 2 mils. They don't leave any, you don't have to guess what error you should get if you use a graduated cylinder, which, by the way, you should never use in a real laboratory if you're trying to make a careful measurement. Likewise, a beaker is even worse. So understanding the instrument tolerances is really important for understanding what error you're going to get out of a certain procedure. And you can almost always find that for really conventional analytical glassware, any chemical glassware, balances, the kinds of things you'd find in a lab. So once you have that information about tolerances, how do you communicate it? Well, you don't want to lie. So the most important thing is when you report out your values, you write them down in your lab notebook, you actually write them down in a way that in a shorthand kind of sense conveys to a reader what your level of precision is. In other words, you don't want to have any false precision in your reporting. So let's take the example of a keychain that might have your name written on it. And you're trying to figure out how much lead is in that keychain. Well, first thing you're going to do is you're going to measure the keychain. Let's say you did it with a pan balance, but what you wrote down in a lab notebook somewhere is 5.1235 grams for that. And we know that's wrong because a pan balance can only measure to plus or minus 0.1 grams. So you're going to be reporting to only the significant digit, the one that you can measure. And let's look at this other example. You did it on a really fancy balance. Well, you know that you know far more information than just 5 grams. If you're using an analytical balance, you should report to the digit of plus, if it goes plus or minus 0.0001, you report to that digit. If it's plus or minus 0.0005, you have a choice to make. You can report to that digit, or you can round up to only the third digit. So these aren't exactly hard and fast rules, but they do help you convey in a kind of quick way how precise your measurements are. And they link to the idea of significant figures. Significant figures are the number of digits past the decimal place. They convey to your reader how precise your measurements are without having to go through a long discussion of statistics. And they really are important to keep in mind because you don't want to over or underreport your precision when you're writing down or typing in numbers from an instrumental analysis. So understanding significant figures, how to manipulate them, is also crucial. But remember, if you're having to ask yourself, well, how many significant figures should I report? The answer is look at the instrument tolerances. How did you make the measurements? And that's going to guide you in telling you how many significant figures you should be using. So I'm going to now take a break, and you can go and watch lecture 4B, which is going to have a lot of examples of significant figures and their manipulation. I would expect for a lot of you this is going to be a review, but if you don't quite remember the rules for sig figs, as they're called, you can watch me go through a couple of examples in the next lecture, which I'm calling 4B.